When installing electrical circuits, especially in industrial settings where long runs are common, voltage drop is a critical factor to consider. The National Electrical Code, or NEC, provides guidelines to ensure safe and efficient operation of electrical systems. Specifically, NEC Table 310.15b16 addresses voltage drop limitations in branch circuits. The NEC recommends that the voltage drop should not exceed 5% of the nominal voltage. For a 120-volt circuit, this translates to a maximum allowable voltage drop of 6 volts. When dealing with long circuit runs, the resistance of the wire itself can cause a significant voltage drop, potentially leading to various problems. These problems can include reduced equipment performance, overheating of conductors, and even premature failure of connected devices. Therefore, it's essential to calculate and mitigate voltage drop to maintain a reliable electrical system. The distance at which you should be concerned about voltage drop depends on several factors, including the load, the wire size, and the allowable voltage drop percentage. For a 20-amp circuit, voltage drop should be considered if the run is longer than approximately 100 feet. However, this is just a general guideline. To accurately determine the appropriate wire size for a specific application, it's necessary to perform voltage drop calculations. These calculations take into account the circuit length, the load current, and the wire's resistance. There are several methods for calculating voltage drop, including using voltage drop calculators available online, consulting engineering handbooks, or applying the following formula: voltage drop equals 2 times the length of the conductor in feet times the current in amps times the resistance of the conductor per foot, all divided by 1000. The resistance of the conductor per foot can be found in NEC Chapter 9, Table 8. For example, let's consider a 300-foot run of 12 American wire gauge, or AUG, copper wire carrying a 20-amp load at 120 volts. According to the NEC, the resistance of 12 AWG copper wire is approximately 1.98 ohms per 1000 feet. Using the voltage drop formula, the calculation would be voltage drop equals 2 times 300 times 20 times 1.98 divided by 1000. This results in a voltage drop of approximately 23.76 volts. Since the allowable voltage drop for a 120-volt circuit is 6 volts, using 12 AWG wire in this scenario would result in an unacceptable voltage drop. To reduce voltage drop, a larger wire size needs to be selected. Larger wire sizes have lower resistance, which in turn reduces voltage drop. For example, if we upgrade to 10 AWG wire, which has a resistance of approximately 1.24 ohms per 1000 feet, the voltage drop calculation would be voltage drop equals 2 times 300 times 20 times 1.24 divided by 1000. This results in a voltage drop of approximately 14.88 volts, which is still above the allowable limit. If we further upgrade to 8 AWG wire, which has a resistance of approximately 0.778 ohms per 1000 feet, the voltage drop calculation would be voltage drop equals 2 times 300 times 20 times 0.778 divided by 1000. This results in a voltage drop of approximately 9.34 volts. While still above the recommended 6 volts, it's significantly lower than the voltage drop with 12 or 10 AWG wire. To achieve a voltage drop within the acceptable range, a larger wire size, such as 6 AWG, may be necessary. 6 AWG wire has a resistance of approximately 0.491 ohms per 1000 feet. Using this value in the voltage drop calculation gives us voltage drop equals 2 times 300 times 20 times 0.491 divided by 1000, which results in a voltage drop of approximately 5.89 volts. This is below the 6-volt limit. In addition to increasing the wire size, there are other strategies to mitigate voltage drop. These strategies include reducing the circuit length, minimizing the load current, and using multiple parallel conductors. Reducing the circuit length is often not practical in existing installations, but it can be considered during the design phase of a new electrical system. Minimizing the load current can be achieved by using energy-efficient devices and avoiding overloading circuits. Using multiple parallel conductors effectively reduces the overall resistance of the circuit, thereby reducing voltage drop. However, paralleling conductors requires careful consideration of factors such as conductor size, insulation type, and termination method. It's essential to consult the NEC and other relevant standards before implementing parallel conductors. In practice, it's generally recommended to use the largest practical wire size that is economically feasible and meets the requirements of the NEC and other applicable codes. Overrating the wire size can provide additional safety margin and ensure reliable operation of equipment connected to the circuit. When selecting wire size, it's crucial to consider not only voltage drop but also ampacity. Ampacity is the maximum current a conductor can carry without exceeding its temperature rating. The NEC provides tables specifying the ampacity of various wire sizes and insulation types. It's essential to select a wire size that has an ampacity greater than or equal to the load current. In addition to wire size and ampacity, the type of insulation used on the conductor also affects its performance. Different insulation types have different temperature ratings, which affects the ampacity of the conductor. The NEC specifies the allowable insulation types for various applications and environmental conditions. In industrial environments, where circuits may be exposed to harsh conditions such as high temperatures, corrosive chemicals, or mechanical stress, it's essential to select insulation types that are suitable for the specific application. Proper installation techniques are also crucial for minimizing voltage drop and ensuring the safety and reliability of electrical circuits. These techniques include making secure connections, avoiding sharp bends in conductors, and supporting conductors properly. Loose connections can increase resistance and contribute to voltage drop. Sharp bends can damage the insulation and reduce the ampacity of the conductor. Improper support can lead to mechanical stress and potential damage to the conductors. When working with electrical circuits, it's essential to follow all applicable safety precautions. These precautions include de-energizing circuits before working on them, using appropriate personal protective equipment, or PPE, and following lockout/tagout procedures. De-energizing circuits before working on them prevents electric shock. Appropriate PPE, such as gloves and safety glasses, protects against electrical hazards. Lockout/tagout procedures ensure that circuits remain de-energized while work is being performed. In conclusion, voltage drop is a critical consideration when installing electrical circuits, especially in long runs or high current applications. The NEC provides guidelines for limiting voltage drop to ensure safe and efficient operation of electrical systems. By calculating voltage drop and selecting the appropriate wire size, it's possible to mitigate voltage drop and maintain a reliable electrical system. In addition to wire size, other factors such as ampacity, insulation type, and installation techniques also play a role in minimizing voltage drop and ensuring the safety and reliability of electrical circuits. Always follow applicable safety precautions when working with electrical circuits. To summarize the key points, firstly, voltage drop is a critical consideration for long electrical runs. Secondly, the NEC recommends a maximum voltage drop of 5% for branch circuits. Thirdly, calculate voltage drop based on circuit length, load current, and wire resistance. Fourthly, increase wire size to reduce voltage drop. Fifthly, consider ampacity and insulation type when selecting wire. Sixthly, use proper installation techniques to minimize voltage drop. Seventhly, follow all safety precautions when working with electrical circuits. In addition to the specific example discussed earlier, let's consider another scenario. Suppose we have a 200-foot run of 14 American wire gauge, or AUG, copper wire supplying a 15 amp load at 120 volts. According to the NEC, the resistance of 14 AWG copper wire is approximately 2.53 ohms per 1000 feet. Using the voltage drop formula, the calculation would be voltage drop equals 2 times 200 times 15 times 2.53 divided by 1000. This results in a voltage drop of approximately 15.18 volts. This voltage drop is significantly higher than the allowable 6 volts. To reduce the voltage drop, we could upgrade to 12 AWG wire, which has a resistance of approximately 1.98 ohms per 1000 feet. The voltage drop calculation would then be voltage drop equals 2 times 200 times 15 times 1.98 divided by 1000. This results in a voltage drop of approximately 11.88 volts, which is still above the allowable limit. Upgrading to 10 AWG wire, with a resistance of approximately 1.24 ohms per 1000 feet, would result in a voltage drop of approximately 7.44 volts, which is also still above the allowable limit. Finally, upgrading to 8 AWG wire, with a resistance of approximately 0.778 ohms per 1000 feet, would result in a voltage drop of approximately 4.67 volts, which is within the allowable limit. Therefore, in this scenario, 8 AWG wire would be the appropriate size to use. In addition to these calculations, it's also important to consider the voltage rating of the equipment being supplied. The voltage rating of the equipment should match the nominal voltage of the circuit. If the voltage is too low, the equipment may not operate properly. If the voltage is too high, the equipment may be damaged. In some cases, it may be necessary to use a transformer to step up or step down the voltage to match the voltage rating of the equipment. Transformers are commonly used in industrial settings to supply power to equipment that requires different voltage levels than the available supply voltage. When using transformers, it's important to select a transformer that is properly sized for the load. The transformer should have a volt-ampere, or VAR, rating that is greater than or equal to the volt-ampere load. The volt-ampere load is the product of the voltage and the current. For example, if we have a 240 volt load that draws 10 amps, the volt-ampere load is 2400 volt amps. The transformer should also have the appropriate voltage ratio. The voltage ratio is the ratio of the primary voltage to the secondary voltage. For example, if we have a 480 volt primary and a 120 volt secondary, the voltage ratio is 4:1. In addition to transformers, other voltage regulation devices may be used to maintain a stable voltage supply. These devices include voltage stabilizers and automatic voltage regulators, or AVRs. Voltage stabilizers are designed to maintain a constant voltage output even when the input voltage fluctuates. AVR are designed to automatically adjust the output voltage to compensate for changes in the input voltage or the load current. These devices are commonly used in applications where a stable voltage supply is critical, such as in sensitive electronic equipment or in industrial control systems. In conclusion, voltage drop is an important consideration when installing electrical circuits, and there are several strategies that can be used to mitigate voltage drop and ensure a reliable electrical system. These strategies include increasing wire size, reducing circuit length, minimizing load current, using parallel conductors, and using voltage regulation devices such as transformers, voltage stabilizers, and AVR. By carefully considering these factors, it's possible to design and install electrical systems that meet the needs of a variety of applications. It's also important to consult with a qualified electrician or electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards.